Hello world! We are Team AuSum from Ledyard, Connecticut, and in this video we are going to show you our AuSum project for this FLL 2017 Hydrodynamic season.
My name's Ben.
I'm Noah.
I'm Gian. And I'm Justin.
This year's challenge was to find a solution to a problem involving the human water cycle. Our problem was to find the easiest way to move water up a hill with minimal power.
We created a few prototypes of a pump that could pump water without electricity and was cheap.
One of our pumps was this Archimedes screw. It has loose coils, and that means it couldn't go up steep inclines.
Our second prototype was an Archimedes screw that had really tight coils, so it was able to pump at a steeper angle. This is a demonstration of our first prototype of an Archimedes screw. As you can see, it has very separated coils.
This is about the maximum we can raise it because of the separated coils. We just got our first drops of water.
This is their second Archimedes screw and has a lot tighter coil.
There's water. Since both of those didn't work too well, we created our final project, the spiral pump.
For our spiral pump, we added a scooper. This allows for more water to be collected and less backflow after we scoop water.
We also used some thick pipe to make our coils. And to hold our coils in place, we used these plastic tube holders and screwed them into these thin pieces of wood. For the tube, we used 2 sections of PVC pipe so we can take it apart for easy transportation. And on the back, we have a universal joint, so this can spin freely and the hose can stay straight.
This is our spiral pump. It worked the best out of all 3 pumps. It has the best flow and can pump the highest.
So from our universal joint, we have the green garden hose. We have it flowing to the front into this bucket. This is where we collect the water and then use measuring cups to measure the amount of water we have collected. As you can see, we have a very big flow compared to the other screws.
This one works the best because it gets us a usable amount of water.
When we added on the scooper, it didn't really change too much about the pump's performance. It just made it harder to turn because it's grabbing more water out of the bucket from below.
We also like the scooper because it stops backflow from the water.
In theory, our pump should be able to pump much higher than it actually does. We were able to calculate the distance we could pump based off of how many coils and the length of the coils we have.
We tested our spiral pump at 5-minute intervals. The first one, we had it horizontal to the water level. It was able to pump 33 cups of water.
And at a 1-foot elevation, or 1 foot above water level, it was able to pump 28.5 cups.
At 2 feet above water level, it was able to pump 7 cups. We tried 3 feet and it didn't work. Our max was 2.5 feet. And the way we could have made it go higher, we could have added more loops to our spiral pump, because the more loops you have, the higher the water is gonna go up.
This is our pump pumping at a horizontal angle, which is the same as level with the water. When we raise it up 1 foot, the stream gets a little bit slower, but it still keeps consistent. When we come up to 2 feet above water level, it's a lot harder to pump. it still gets water. 2.5 feet is our top point where we still get tiny drops, but barely anything to use. When we lower it again to 2 feet, or even to 1 foot, it starts pumping water again.
This concludes our presentation about our project.
We hope you learned something about water pressure and elevation.
Wacko, wacko, wee, woo. Wacko, wacko, wee, woo.
I need to get some.
Yeah.
Ah!
Go like underneath.
Oh my god! Dude, they're probably poison. Stop! You're wasting the water! No, we need it for the water slide!
You might want to move it. Okay, I need to get in here.
No!
No, not like straight up. You miss everyone.
No.
You had like no